All right, folks, today we are introducing day 4. This is on special right triangles. It's a couple of different scenarios that we're going to be inspecting over the next couple of days. Today is the case of the 45-90 right triangle. So that is a case where we have a right angle, so my 90-degree angle, and then my other two angles are 45 degrees each. That's going to set up special ratios that exist between the sides of the triangle so that we're actually able to solve for unknowns with a shortcut, more or less. So before we get into that, we are going to have to revisit rationalizing the denominator. This is just a skill that we will use when we are simplifying answers. Just by default, we don't like radicals in the denominator. We don't like to keep that there. So there's a process to eliminate that radical from the denominator, and it's the process of matching that radical. So I'm matching it with another root 4, and I have to multiply to both the top and the bottom, because any change I make to one side of my fraction, I have to be consistent and make it to the other. So in doing this, I end up with a 5 root 4 on top, and on the bottom I have a root 16, which just simplifies to 5 root 4 over 4. So even though the answer doesn't look any simpler, as a matter of fact, it looks a little more complex than we started with, it's just a common practice that we don't leave the radical in the denominator. Okay, so same thing with this next one. We want to match that radical, get rid of the root 2, top and bottom. So I end up with a 4 root 2 over root 4, which is just 4 root 2 over 2. And then in this case, I'm trying to simplify. Notice that 4 and 2 are both divisible by 2. So if I divide the top by 2, I get a 2 root 2. And the bottom, the denominator divided by 2 is just 1, so we would leave it as such. Okay, next guy, again, we're matching that radical, get rid of the root 3, top and bottom. So we have a 3 root 3 over square root of 9, which is just 3 root 3 over 3. Notice here my 3's cancel, so I just have a root 3. Okay, one more, trying to match that radical with a root 3, top and bottom. On the top here, we're multiplying this hybrid term by the radical, so the 3 just hangs out in the front, but the 2 and the 3 incorporate as a root 6, and then on the bottom there, root 9. So I'm looking at 3 root 6 over 3. 3's cancel, leaving me with root 6. So we'll be using that skill in simplifying our answers today. Okay. Also a little bit of recap on ordering sides and angles from shortest to longest. But in this case, the context of a 30, 60, 90. So we know if we have a 90-degree angle with 60, that leaves 30 degrees for my angle budget of 180 degrees. We know that as far as the angles go, that's probably a little bit easier to start with. Angle, and we said from shortest or smallest to largest. So angle P is the smallest, then angle M, then angle N. Remember that the sides that are across from these would be corresponding in the sense that they are also going to be the shortest to longest, that kind of same escalation there. So P is across from side MN. So that's my first one there. 60 degrees, angle M is across from side NP. And then 90 degrees is across from MP. There we have it. Okay. Similar practice here. Notice that we have 90 degrees. And then in this case, we have 2 of our angles unknown. But if you notice that we have a 6-inch side and an 8-inch side, so the one across from the 8-inch side has to be the medium angle, right? And then across from the 6-inch side, that would be my small angle. So if I'm ordering these, angle C is the smallest, angle B is the medium angle, and angle D is the largest. And then the sides that correspond, the ones that are across from small, medium, large angles, would be side DB, and then side CD, and then side CB. And that will come into play again today in these ratios that we're going to introduce. Okay, so to kind of a little summary here, in a right triangle, the largest angle, well, let's see. Let's see if we can kind of work this backward. We know that the largest angle will always be opposite the largest, or the longest, we should say, longest side. Longest side, okay, which is the hypotenuse. Largest angle, I was assuming I was I knew all this terminology here. We're going to check that really quickly. Largest angle. Pretty sure it's just, oh, well, no, it's not that. If it's large, we just say if it is larger than a right angle, then it would be obtuse, but I don't think there's a specific term there for that. We just say that it's the longest, it's the largest angle. Smallest angle will always be opposite from the shortest side. Okay. Oh, well, here's what it was. In a right triangle, that was the part we were missing. The largest angle, or the right angle, that's going to be the largest in the right triangle. It's like, what is the vocabulary term on that? Here we go. So we're set. Okay, so now let's introduce the rules for the 45, 45, 90 degree triangle. This is a special set of ratios here. So if we are getting a larger, if we're getting larger as far as like escalating from small to medium to large, then we will be multiplying by a scale factor in a sense, because there's a consistent ratio amongst the sides for these types of triangles. If we're getting smaller, so we're going from like long side to medium to and so forth, then we will divide. And this holds for 45, 45, 90 or 30, 60, 90. Okay, these ratios right over here demonstrate the relationship. So notice that in a 45, 45, 90, my two sides across from 45 degree angles are congruent. We designate those as just x. So they are in a one-to-one ratio. If I know the measure of those legs, then I can find the measure of the hypotenuse, which is longer and across from the right angle, and that is just modeled as x root 2. So I literally just multiply by root 2 if I'm going from leg to hypotenuse. Okay, so just to kind of organize this process, if we have a leg and we want the other leg in this type of scenario, 45, 45, 90, we just keep the value of x. So if we know that one leg is 12, then the other leg has to be 12, because those are going to be congruent measures. If I have a leg, which remember we're designating as x, and I want the hypotenuse, which we're designating as x root 2, then we multiply the x value by root 2. On the other hand, if we start with the hypotenuse, which we're designating as x root 2, and we're ending with the leg, which is x, then we want to divide the hypotenuse length by root 2. So it's kind of, there's a directionality element, and then you want to know just that ratio of 1. Let's just kind of summarize here. 1 to root 2 as far as leg to hypotenuse. It's kind of like an extended ratio. Okay, so first scenario, we want to find the hypotenuse given the leg. So first off here, what do we have? We know that, and notice here, this is where the nomenclature gets a little confusing, because they're naming the hypotenuse x. So it probably would even be better if we go back up here just to revisit this, and just because x is used so often in the diagrams, like scrub it for an A, and an A root 2, and then you're less likely to get into that point of confusion. So you could even swap all of these out as well. But if we know that that ratio of 1 to root 2 exists between leg, and hypotenuse, then I can just go ahead and throw down my ratios of A root 2. And that's going to kind of clarify some of that confusion there, so I don't have contending variable definitions. So in this case, what we have, we know that the leg A has a length of 2, and we want the hypotenuse as the prompt was asking us for. So we know if we're going from leg to hypotenuse, we're getting larger. Okay, I guess we'll just do the work up here. So if we know that A equals 2, that's literally just by our designation here, then my hypotenuse, which is A root 2 over here, would be 2 root 2. Right, so my hypotenuse, I feel like this isn't organized very well. Let's just go ahead and add here that the hypotenuse is 2 root 2. Okay, so again, if that helps to kind of change out the variables just for A, then you don't get contending x's there. Okay, next one again, notice it's a 45, 45, 90, so we know that the leg to hypotenuse ratio, 1 to root 2. In this case, what we have is a leg, once again. Okay, so we know that the leg equals 11. And we want the other leg in this case because they're asking us for y. We're not getting smaller or larger. These are actually the same measure. Oh, no, misspoke on that. Whoopsies. That's a hypotenuse. That is the hypotenuse, okay? So again, if it helps to just designate A, we know the ratio of A root 2. Then if A is 11, we can organize it like this. If A equals 11, then A root 2 equals 11 root 2. It's not too bad, right? So my hypotenuse equals 11 root 2. And it got larger because we went from the leg to the hypotenuse. Okay, now we're going the opposite direction. We're going to find the leg given the hypotenuse. Okay, notice that they're already setting us up with the kind of the x dynamic. So we could just keep it as x, and so forth. But in this case, we know that we have the hypotenuse and we want the leg. So now we're working backward. We know we're getting smaller if we go from a longer side to a shorter side. Okay, and remember we're designating this as x root 2. So let's go ahead and model it as if x root 2 equals 7 root 2. Notice how easy this is to just compare that the x is a 7, right? So we can say then x equals 7. And that is the length of my leg there. So my leg is 7. Okay. Next one, still a 45, 45, 90. We know we're still finding the hypotenuse when we are given the leg. Okay. We know that the leg in this case, wow, the directions don't even, oh yeah, no. But we have the hypotenuse. Goodness, guys, I'm not very good at filling in blanks for some reason. So what we have the hypotenuse, we need the leg. The hypotenuse from our diagram is 16. Okay, if we throw down the labels there, as your A root 2, right, we can say if A root 2 equals 16, then notice we're going to have to solve for A. So let's write this out again. A root 2 equals 16. So I'm going to have to divide both sides by root 2. These cancel here. This is where my rationalizing comes into play. So if I have 16 over root 2, I like to get that denominator cleared of those radicals. So I'm matching it with a root 2 top and bottom. So I'm going to have a 16 root 2 over 4 root 4, which is 16 root 2 over 2. And that simplifies to just 8 root 2. So I can find that my leg is 8 root 2. Okay, so again, guys, being consistent with yourself on like how you approach these will kind of help, because otherwise it can get kind of overwhelming to try to remember the rules. But just naming those the legs and hypotenuse right out of the gate kind of gives you some guidance. Okay, so next we went to solve for the variable in the following right triangles. So we kind of took the training wheels off here. It's not quite as structured. So if we want to solve for x, again, let's throw down our a's. X is at the hypotenuse, right? And we know that makes these guys the legs, and this is the a root 2. Okay, so if we know, in this case, we're given the leg, so we're getting larger to find the hypotenuse. So again, we can say if a equals 12, then a root 2 equals 12 root 2. Right, so, oops, this is actually my hypotenuse length, and because it was defined as x in my diagram, that is my answer. It's 12 root 2. Okay, next guy over here, we're looking for z. Okay, based on the diagram, that's again the hypotenuse, so we can throw down our labels, a root 2. So we know if we're going from leg to hypotenuse, we're getting larger. Okay, so let's say that if a equals 6, because that's literally defined for us, then a root 2 equals 6 root 2. That's, again, my hypotenuse, and that was labeled in my diagram as z, so that is my answer. And I think that continues, still solving for the unknowns. Notice that they took some of the markings off, but if we know that these angles are congruent, these have to be 45. So we still have the 90, 45, 45 scenario. So let's just throw down our A's, right? We know this guy's an A, this guy's an A, this guy is an A root 2, right? So we can say that if A root 2, because that's defined for us, equals 5, let's solve for A to then find X and Y. Then if we clear this, A root 2 equals 5, so I know I have to divide both sides by root 2 in my process of solving for A. So A would equal 5 over root 2, but we want to rationalize, multiplying top and bottom by root 2. So I would have 5 root 2 over root 4, which is 2. Okay, so this is my A, but not only is it A, it's like literally these are interchangeable. X is the same as A, Y is the same as A. So we know that both Y and X are equal, so X would equal Y, which equals 5 root 2 over 2. And that would be your final answer. Okay. This guy, similar scenario, we have the 45, 45, 90. And in this case, we throw down our labels. We have our A, root 2A. All right, and I keep switching that around. Root A, root 2. So we can set up our logic here. If A root 2 equals 6, we know we have to solve for A. Divide both sides by root 2. A would equal 6 over root 2. We have to rationalize our denominator, so multiply top and bottom by root 2. Giving us A is 6 root 2 over root 4, which is 2. And that would simplify as just 3 root 2. So that's A. Again, they were asking for X and Y. A literally equals X, which literally equals Y. They're all substituted or interchangeable. So that is our answer there. So if I add it back to my diagram, because sometimes the visual helps too. This guy is, what did we say? 3 root 2. 3 root 2, 3 root 2. Okay, last one. We know we have 90 degrees and 45 degrees, leaving the other guy as 45, 2. Throw down our labels. We know this is A, this must be A root 2. So in this case, we're saying if A equals 12, then A root 2 has to equal 12 root 2. And that is the same as X. So literally, X equals 12 root 2. Okay, so that's the process, just kind of knowing the ratios and how to apply either through division or multiplication.